Hi folks, welcome to Impulse and Momentum. What we're looking at today is a review of what we covered in class today, as well as going into a lot of depth looking at collisions. Momentum and impulse. Remember momentum, the symbol for momentum is P. That means that the equation that we use is P is equal to mv, meaning momentum is equal to mass times velocity. Remember, momentum is simply mass on the move or inertia in motion. The unit for momentum is kilogram meters per second. Kilogram is our unit for mass. Meters per second is our unit for velocity.
Not enough momentum.
Now, as Mr. Nye was mentioning, the ping pong ball does not have enough mass or velocity in order to knock over the pins. Let's see how well you do calculating the momentum of a 2,500 kilogram truck, either moving at 18 meters per second or parked in a driveway. How about a 0.13 kilogram baseball, which moves at 36 meters per second? Just as a reminder, momentum is mass times velocity. Manipulating our equation, we can also figure out how fast we can figure out the velocity of a 7.3 kilogram bowling ball. Now, if these three equations made good sense, then you are ready for us to look at impulse. If they did not, please go back and review them, review your notes from today, or check out the video at the end of this video. An impulse is required to change the momentum of an object in order to either speed it up or slow it down or change its direction. Let's take a look at how we figure out what an impulse is, because we know that a change in momentum creates an impulse. So we know that forces are required in order to create an acceleration. Now, we know what a force is and we know what our mass is. And if you'll recall back, the acceleration equation is change in velocity over time. So if we replace our acceleration in Newton's second law with our change in velocity over time, we can see that force is equal to mass times the change in velocity divided by time. Hey, look, there's mass times velocity. That's momentum right there. If we isolate momentum, we can figure out that an impulse is the force multiplied by the time, and that will give us our change in momentum.
Family of baseball players, I think that's what kind of got me into it. Coming up, my biggest motivator was fear. Fear of maybe not living up to expectations, or maybe fear of not being able to play with, guys that are bigger than you.
This pitcher follows through on the pitch to increase the ball's momentum and make it travel faster. The key that we're looking at here is that time and velocity are directly proportional. Therefore, if we increase the time of contact, this will increase the velocity. That means that following through keeps the ball in contact with the pitcher's hand for a longer period of time. This will give it more velocity and, by definition, more momentum. Think of another scenario where this might be the case. How about the reverse? Why does a batter stop the bat when bunting? If your guess is because it reduces the amount of contact time with the ball, therefore reducing the amount of momentum, you're on the right track. Let's take a look at this scenario. Which would do more damage, stopping a truck moving at 60 miles an hour by running into a brick wall or a haystack? Now, some of you may think that it's going to be the same, but this is where we need to really take a look at this idea of momentum and impulse. The change in momentum in either case must be the same. We must take our vehicle and have its motion of 60 miles an hour drop down to 0. Now, if we use the brick wall, that momentum change is going to happen in a very short, small period of time. This means the force involved must be huge, as opposed to going through the haystack, where the time is going to be much extended, meaning that the force is going to be much smaller. Now, if all of that makes sense, let's take a look at what happens when things come together. There is a law of physics called the law of conservation of momentum. Now, this is a very important idea. In this law, we understand that the momentum of a closed, isolated object or system of objects does not change. That means that it is not increased, it is not decreased, that the momentum before a collision in a closed, isolated system will be the same as the momentum after the collision. Let's take a look at what some of these terms mean. When we say system, we're referring to a collection of objects. When we talk about an isolated system, that means that no net external forces act upon this isolated system. And a closed system means that no objects enter or leave. So if I'm talking about a ball and the floor, that is the closed system. No objects must enter or leave that system in our consideration. So this is a law, meaning that we can use this information to help us better understand other physics concepts. Now, before we can really look at types of collisions, we need to learn about types of collisions. First of all, there are elastic collisions. In an elastic collision, objects will bounce off each other without deforming or losing energy to heat. Now, when we're talking about something that is elastic, we oftentimes think about things like rubber bands or things like that. But in reality, the objects that have the greatest elasticity are things you wouldn't generally think of. For example, steel has a much, much higher elasticity than rubber does, because steel will return to its original shape without deforming or losing energy to heat, whereas rubber actually experiences quite a bit of deforming. Let's take a look at some pool physics. Now, as you saw on the pool table, each pool ball was able to transfer its momentum into a pool ball next to it. Now, collisions are rarely completely elastic, and some energy is almost always lost to heat. Only collisions between molecules of a gas are nearly completely elastic. The other type of collision is called an inelastic collision. And this is where objects will stick together or are significantly deformed with a loss of energy to heat. Let's take a look at some inelastic collisions. In either case, momentum is conserved in all types of collisions, regardless of whether they are elastic or inelastic. This means that the momentum, the mass times the velocity of your objects before the collision, will be equal to the mass times the velocity of your objects after the collision in your closed and isolated systems. All right, did you get it? Let's take a look. Let's see if you can answer this question. A massive football player sitting on the bench has a large momentum, small momentum, or no momentum. What do you think? If you said no momentum, I think you have a good understanding of what momentum is. Because remember, momentum is mass in motion, and if he's sitting on the bench, there's no velocity. No velocity means no momentum. How about this one? An impulse equals the force applied times the time of application, creates a change in momentum, both A and B or neither A and B. What do you think? If you guessed both A and B, I think you have a good understanding of impulse, because impulse is the force and the time of application, and it does change it does create a change in momentum. How about this one? When the time of an impact is extended, the force is What do you think? If you guessed decreased, then you've got a good understanding. Let's take a look at collisions. In a closed, isolated system of objects, what of these applies? The answer is all of them. In a closed, isolated system of objects, no object enters or leaves, there are no external forces, and the total momentum cannot change. It must be conserved. All right, that is your video for today. I recommend that you review this information until it makes sense. Attached, you will find some problem sets. We'll see you in class.